hate to say it, but cosmology is one of those fields where the mysteries only seem to grow the more we learn. It can be extremely frustrating, but it's also tons of fun. We're still grasping at the elusive nature of dark matter, wrestling over the persistent Hubble tension, and grappling with the puzzle of baryon asymmetry. And most of all, puzzling over one of the most frustrating questions of all. Is dark energy truly behind our universe's accelerated expansion?
And that's what's frustrating, because I can't imagine how this problem can be solved.
Luckily today, we are blessed with one of the most brilliant minds in the universe, George Efstathiou, a professor at the University of Cambridge and the first director of the Kavli Institute for Cosmology. Today, he shares some counterintuitive wisdom that absolutely blew me away.
If your theory agrees with all of the observations, then it's bound to be wrong.
He's joining us today to drop some more Big Bang-sized truth bombs on us, to address the anxieties, tensions, and curiosities that plague cosmology, but also make it the most fascinating subject imaginable. So let's get to it.
First, I want to ask you, George, I always ask people, what's your favorite day on the calendar? For you, I think it might be in September, but the reason I ask that is because the origin of your birth or of some significant event is always, something special. And so I want to ask you about your origin story starting back some decades ago. So tell me, please, what's your past world line look like?
It's quite interesting. My parents were both born in Cyprus and moved to the UK after the Second World War. So my father came in 1949 and my mother came a couple of years later, and they met in the UK. And at that time, Cyprus was a British colony, and the Brits were looking to the colonies, come to the UK and help rebuild the motherland after the war. That's how my parents ended up here. So as part of this, quite significant migration of people from former British colonies to Britain. So before then, I mean, my father was my father's family. They were farmers in Cyprus, and my father eventually set up a business as running a fish and chip shop in one. And so when I was a kid, I used to work there at the fish and chip shop. So there wasn't this sort of academic background to the family. I was always interested in astronomy. I mean, one of the I think one of the reasons that I got into astronomy professionally was because I never grew up. You ask these fundamental questions as a child, and I'm still working on those fundamental questions. So there wasn't a history of academic, going to university and so on. But I got motivated for a really weird reason that I decided I wanted to go to Oxford, and the reason for that, there was a TV program called The Persuaders with Tony Curtis and Roger Moore. So they played these sort of playboys, sleuths, solving various crime problems and so on and so on. And the start of it, the Roger Moore character Brett Sinclair was from a wealthy family and went to Oxford. And from the credits, I thought that's what I want to do. I want to go to Oxford. So it became a sort of ambition, and eventually I did end up going to Oxford, and then launched into a research career.
When I look at your career, it's kind of what resonates with me is this notion that you're kind of unafraid. You're courageous in your approach to taking on the orthodoxy when necessary, and sometimes being slightly controversial or how do you say it there? I know you say controversy, but do you say controversial?
Yeah,
when I was in the UK last summer, you were busy, and I should mention you're one of the treasured members of the Simons Observatory External Advisory Committee, which is something that we lacked with our BICEP experiment. We didn't have guardrails, checks and balances. We didn't have a kitchen cabinet or war cabinet, however you want to phrase it. And so your insights have been invaluable there. But I want to ask you, you're kind of known for taking on these grand challenges. When you look at something which I spoke about this summer at the Royal Institution, which was the question, was there a Big Bang? And there's a lot of kind of commentary from many people, some are experts, some are not, that either the Big Bang didn't happen or that it happened essentially twice as long ago as we naive cosmologists would assume. How do you separate the orthodox kind of challenges that you are taking on with anomalies and Hubble tensions and sigma 8 tensions and stuff that we'll get into? How do you separate that from what might be considered to be, baseless claims about the non-existence of the Big Bang? And as I made a joke, I said, if there's no Big Bang, you don't need a big banger. And I showed a big sausage. Yeah. So go ahead.
So on controversy, I don't court controversy. And in fact, the people have accused me of being far too orthodox. That I defend the standard model of cosmology, lambda CDM, to the death, and you just have to look at some recent articles like the one by Brent Tully, where he actually names me as as somebody who has reminds him of Sandage and Taman, who wouldn't accept the key project value of the Hubble constant. So we'll probably talk about the Hubble constant. So I think it depends on your point of view. I mean, the problem with that is that people don't I think understand when we got Planck data of how extensively I tried to break the lambda CDM model, and I just couldn't do it. It just wasn't possible. So it's not for want of defending a particular cosmology. It was the I'd have loved. I mean, you know that in science that you do big experiments and you find a massive discrepancy with what everybody accepts, then that's a big result. Okay, so it wasn't for want of trying. But as for, I'm actually worried, and I'm wondering whether it's a function of age, actually, about people getting a lot of publicity for very weak or outlandish ideas. And this is an increasing trend. I encountered this just this week because you've probably seen articles or reports of the discovery of a big ring in the sky. Now, this is MG2 absorbance, so absorption lines from quasar spectra, and this has been reported as an enormous structure in the universe that disagrees with the standard model. Just look at the data; it's incredibly sparse. I don't think that there's a. It's very difficult when you're dealing with sparse data. It's always difficult to deal with look elsewhere effects. You see a pattern, and how do you assign a significance to it once you've seen it? And when I first looked at the picture of the MG2 absorber distribution on the sky, I wondered, which ring are they talking about? Because I could see seven. But this has made it, into New Scientist, into,
Sky and Telescope here in the US.
Yeah. And, it seems to me, incredibly weak. And then you can get even more outlandish theoretical ideas. I mean, the observational thing, okay, fair enough. They've pointed this out, but, it's not very convincing. But then on the theory side, just have a look at some of the things that have, appeared recently. Like, we make a model based on MOND that changes the growth rate of fluctuations so that we can get enormous voids, and that this fits in with the big ring, and the voids can explain the anomalous value of the Hubble constant, and so on. And that now you get into really outlandish ideas, and it's published.
Yes.
You see, so and this worries me, because it's creating, something that is that idea, the Mond idea, conflicts with so many things that we know. But it's yet I was asked to comment by a journalist, from New Scientist about the Mond paper. And I was very busy, and I just wrote back quickly saying, really, New Scientists, there's plenty of good science that New Scientists could be reporting. Why are you giving fuel to these kinds of ideas? And I said, if we live in a world where people have created alternative realities, politicians have created alternative realities, we really shouldn't be doing this as scientists. Okay, so the journalist didn't take kindly to that remark, but it does bother me. It does bother me. There are these sort of alternative realities, and you can't engage when it becomes when the different perceptions are so different. You can't engage. We're struggling as cosmologists, as scientists. We're always struggling with the fact that there are some observations that don't fit. Okay, I mean, a quote that I've used for decades, it is apparently attributed to Francis Crick. And he said that, if your theory agrees with all of the observations, then it's bound to be wrong, because at any one time, some of the observations will be wrong. And that's what we're struggling with is trying to make sense of things we don't know, whether, this particular observation is right, this isn't right. So we're constantly mud wrestling. We're having to make these judgment calls. So on the theory side, we have, over the, many, many years developed this kind of intuitive feel that, an elegant idea is likely to be more right than one of lots of bells and whistles that could adjust. Okay, so simplicity and beauty is a guide to assessing theories, and of course you can phrase that thing, that concepts in a statistical jargon if you want to. But on the observational side, it's then a judgment call, very subjective judgment call on what to ignore and what not to. And that's where we get a lot of controversy.
Hey there, fellow explorers of the universe. I hope you're enjoying this cosmological voyage with none other than my hero, George Efstathiou himself. It was a really fun interview, and I hope you appreciate that I don't always bring guests that are household names like Neil deGrasse Tyson or Brian Greene or Sam Harris. Sometimes I bring lesser known individuals, but they're not lesser luminaries. These are some of the most brilliant minds in the known universe. If you want more of them, please do join this channel. Please do subscribe to this channel or follow the podcast on your podcast app player of choice. Only about half of you are doing it, and that's a number even more mysterious to me than the puzzle of dark energy. So once you do it, that'll clear up that dark matter for me and allow us to get back to having more exciting conversations just like this. Now back to George.
Very underappreciated, right? That you can, I mean, in the social sciences, there's at least a name for it, p hacking. We don't really have that, but there is a tension in that we, no pun intended, that we have a singular cosmos, at least for now. I want to talk about the multiverse later, but there is but one cosmos, there is but one universe from which to draw information experimentally and empirically. So when you're in such a situation, unlike even astronomers who have, literally 10 to the 20 stars in the observable universe, we only have one universe to study. So I always found that puts us at a disadvantage in that we kind of tend to overinterpret things, and maybe, just maybe, we're reaching here to find tensions and so forth where they're not. And I guess I wanted to pivot to the Hubble tension. I've had Adam Rees on many times, And I wondered, it would be impolite if I didn't allow you, as one of the foremost experts in this, to explain it from a technical point of view. My audience is highly technical, the most brilliant audience in the known universe. So please start with the high level. As a professional, as someone working in this front, we see respected astronomers disagreeing. I've often said we have so many tensions that we need a good therapist for the field. How do you view the Hubble tension?
The Hubble tension, the Hubble tension is a really interesting. It's a really interesting problem. Let me say at the moment that I don't know the solution. I mean, I'm agnostic. Okay, so what I do have is a tremendous amount of respect for Adam Rees and his team and the work that they've done. I think they've done beautiful observations, lots of consistency checks, and so on and so on. So, but just to explain my perspective, we have a standard model of cosmology that's specified by 6 parameters, and it fits a range of observations beautifully, and in particular the cosmic microwave background. And so from observations of the cosmic microwave background, this model gives us a value of the Hubble constant of about 67.5 plus this about a half. So, and Adam Rees with direct detection measuring the distance scale with a distance ladder. So this uses a combination of geometric distance anchors, then Cepheids, bootstrap out to Cepheid measurements of galaxies that host it as a type 1a supernovae. And then you go to cosmological distances, assuming that supernovae is standard cavs. So it's quite an elaborate distance ladder. And they get 73 plus or minus 1. So the tension, the discrepancy is 5 sigma. Now, the reasons I think that you have run into difficulties is that, the cosmic microwave background, those results for that model is secure because we have, predecessor of Simon's and the South Pole Telescope with independent measurements of the cosmic microwave background. Independently of Planck, they give the same. So there isn't a problem with the observations of the cosmic microwave background. So I think that side is secure. Then what you can do is you can construct an inverse distance ladder. If you have measurements, another geometrical measurement, so from galaxy surveys, you can measure a geometric scale that comes from the oscillations of baryons when the universe was highly ionized. That gives you another geometric distance measurement, and then you can infer from, if you calibrate the BAO measurements using the CMB, you can infer a value of the Hubble constant. So that's called an inverse distance ladder. That gives you about 68, consistent with the cosmic microwave background. It depends on a normalization, which tells you the physical scale of these oscillations. So you can argue that maybe that's wrong, and that's most of the so-called solutions of the Hubble tension have altered that scale. So it's the maximum distance that sound waves can travel from the beginning of the universe to the time of recombination. So we call it the sound horizon. But independent of any sort of measurement of the sound horizon, you can use primordial nuclear synthesis and infer a sound horizon, and that also agrees with the CMB. So you have a situation, you've got to try and come up with a mechanism for the sound horizon, then you have to fiddle around with nuclear synthesis. And if you don't, then you have this problem. So you're caught. You can't modify the late time physics. You can't modify the early time physics, and so you're caught. So that's why, from the theoretical point of view, it's really interesting because it's difficult to know how you can solve this problem. So a lot of people have looked at solutions that alter the physics somewhere in the middle. So you can imagine, so this is a class of models called early dark energy. you can imagine having a field. I mean, I discussed this sort of thing within the Planck collaboration a long time ago, and I called it the confusion field because its only purpose in life is to confuse us about the value of the Hubble. Said it as a joke, but people have studied these models, and recently I wrote a paper with Vivian Poulin and Eric Rosenberg, where we use an improved analysis of the Planck satellite, and it really disfavors it. That doesn't work. So I don't see any good solution. So could it be a problem with the Cepheids? In the last year or so, the recent collaborators have got data on maybe five now galaxies observed with James Webb Space Telescope, and so with James Webb at these infrared wavelengths, the resolution is so much better than the Hubble Space Telescope that the photometry is much easier, and they find exactly the same answers as they did with the Hubble Space Telescope. So there's no obvious problem with the photometry. So if they're wrong, then it's a real conspiracy of a number of things that have evaded tests. So it becomes contrived. I mean, so I was in Munich giving a series of lectures last summer, and coincidentally, Adam Rees and colleagues were in Munich at a separate conference on the distance scale, and they called me in and showed me the new JWST results. I was sort of flattered that they wanted my seal of approval, in some way. And they presented this stuff, and then they said, "Well, what do you think?" And I said, "Well, it's really impressive. So I'm just going to park the Hubble tension." And their reaction was, "What? You think you're going to park our data?" And I said, "Well, we need a theoretical framework to interpret things, and I just don't know what to do with this, So I'm going to park it, and don't feel too bad about it, because in our standard model of cosmology, we've parked the problem of dark matter, we've parked the problem of dark energy, and we've parked the problem of inflation. So there's just another thing to park, So, but it is frustrating. It is. I would really like to know the answer. If it's a theory, if theory is wrong, then it's wrong in a really bizarre way that our universe mimics lambda CDF. Really exquisite. Though it's just uncanny. So very profound. If it is a theoretical explanation, if it's a data issue, then I don't know what sort of data issue it could be.
When we look at some of your recent papers, including one of my favorite, to H naught or not to H naught, and then that investigated whether late time physics could account for it, the resolve the Hubble tension, finding that no, it couldn't. So that's let's say you get a letter from God, and God tells you to accept what Sir Arthur Eddington, I believe your countryman, once said: never trust an experiment until it's been confirmed by a theory. It seems like you in that paper and then with your colleagues and students have ruled out at least half of the available parameter space, or in a binary sense, but probably in terms of the elapsed time since the universe's history, it's probably 99.9% of parameter space. So what hope is there other than to look at early times? And that's where I want to turn next. Your papers on Axion-like dark energy. How could that potentially solve it? And then I'll present you with a couple of my favorite.
Right. Well, I don't think it solves it. It really.
I should say, George, by the way, this is what I love about you. You're not afraid to propose bold ideas. You're not afraid to mix it up with your colleagues, but you're equally likely to say that you're likely to be wrong. And I think just for my students out there, there's hundreds of thousands of students that listen to this. That's the mark of a good scientist. Not to say, yes, aha, eureka, I have found it, as as Archimedes would say. But no, to say, wow, that's really weird, and I'm doing my best here, and I don't know. I think I don't know are the three most important words for a scientist. But we'll get into education later. So,
It's maybe a consequence of a very long career in which I've been wrong lots of times. So learn from experience. But there is an important point, okay, which is the to always maintain a level of modesty, because I'm not as clever as the universe. It's so what I think doesn't really matter. I mean, things could be much stranger, and that's what's frustrating, because I can't imagine how this problem can be solved.
But you say axions are not likely, even though this is something that people...
I mean, it's introducing a new field, and it really is. The only purpose of it is to confuse us about the value of the Hubble constant, because one of the features, it can't be a sort of standard axion-like potential. You have to adjust the potential so that this component becomes dynamically negligible at the present day. Otherwise, you'd be able to rule it out from late time measurements. So you have to start playing around with the potential so that it really does just affect the sound horizon. And the models don't work very well anyway. And the motivation for the project with Vivian and Eric was that if you have a theoretical idea that is, 2.5 sigma is disfavored at, say, the 2.5 sigma level, you don't have to make much of an improvement in the data to turn that into a 3.5 sigma level, because you're already on the tail. You should always be on the lookout for theories or things that are nearly ruled out. Because if you find things that are nearly ruled out, you can maybe do something. And, if you're already on the tail, you can do something that just pushes it over the edge. So that's what happens with early dark energy. It wasn't favored to begin with, and then you can improve the analysis of Planck, and it becomes even more strongly disfavored. And that's another thing that really bugs me, because since Planck collaboration disbanded in 2018, and then I started some projects of trying to squeeze more out of Planck, and everything that I've done on this has just made the data. It brought the data into even closer agreement with the 6-parameter lambda CDM model. Okay, so no sort of anomaly or hint of something that was looked to be 2.5 sigma here or whatever. None of that has got stronger.
When I look at the Hubble, tension is not really, where the bread is buttered around the Keating household. I'm more interested in much more, kind of primitive and primordial concerns, although it's obviously incredibly interesting. My favorite one is primordial magnetism and primordial magnetic fields. And I want to segue into that because, when do I have a chance to talk to an eminent expert who's written about all sorts of things? But the reason I like magnetic fields is because it's the only thing that doesn't require new physics. We would especially be secure, as having lectured in the place where Michael Faraday did his work on magnetic fields and the Faraday effect and all sorts of other cool things, to have the combination of lambda CDM with early magnetic fields that themselves could reduce the sound horizon. So first, if you could opine upon that, I like it because, as I say, it doesn't rely on chameleon fields or evolving dark energy that's not a cosmological constant, which we have no evidence for. So what do you think about this as kind of a field? It doesn't seem to get much attention. My good friend Levon Pagosian.
I mean, we had in the Planck papers, we had we did some analyses that set constraints on primordial magnetic fields. But there was no evidence for primordial magnetic fields. I mean, it is an area that I haven't worked on, and I think primarily it's because I've had a background in, sort of, galaxy formation as well. And, I used to work on those sorts of problems. And the idea that you need, I was never bought into the idea that you needed primordial magnetic fields to seed the magnetic fields in galaxies. I always thought that was the primordial magnetic fields that you would have would be very small anyway, but you can generate the magnetic fields, spontaneously, and then amplify them, through a galactic dynamo. So I wasn't, I never bought into the idea that you needed primordial magnetic fields.
So in terms of another tension, and another reason I sort of favored the, magnetism playing some role was that there would be potentially a concomitant solution of the sigma 8 tension. Can you talk about that? Which of the two tensions, obviously Hubble gets a lot more attention from its tension, but talk about sigma 8 and why, again, how, magnetism seems like, it could do two, it could be the peanut butter and chocolate that solves two problems at once. But I'm sensing a little bit of pessimism on your part.
Well, no, I think that the sigma tension will be, we will pretty much know the solution basically definitively in a few months.
How so?
Okay, so just to explain, I mean, the sigma 8 tension is that some measurements give, so sigma 8 is a parameter that depends on the amplitude of matter fluctuations at the present day and the value of the matter density parameter. So gravitational lensing measures a particular combination reasonably accurately. And so this combination of parameters, turns out to be low from gravitational lensing. So people have interpreted it as some sort of late time effect that at late times the fluctuations have grown less slowly, so more slowly than predicted by lambda CDM. Maybe there's some modification to gravity, something that affects the growth rates, and so on and so on. That's the tension. Okay. So is it a late time effect? Well, I worried about this because I think it's a good example of where I was motivated by patterns in the data. Okay. So is there something wrong with the growth rate, the fluctuations at late times? Well, if we look at some things that I think are uncontroversial, we measure gravitational lensing from the cosmic microwave background, and we measure it really accurately now. And there's no evidence for any change in the growth rate. Okay, it's also interesting because in modified theories of gravity, photons see a different potential compared to the matter, depending on the type of modification to gravity. Whereas in general relativity, they see exactly the same potential. So there's no evidence for anything that departs from general relativity. Photons are doing what they should be doing according to general relativity. So that says, and now that's sampling things down to redshift of about 2. There's no evidence of any discrepancy there. From galaxy redshift surveys, you can measure the rate of growth of fluctuations by looking at the anisotropy of the galaxy distribution in redshift space. You can measure redshift space distortion. Those measurements also don't conflict with the standard model. There's no evidence of any funny behavior there. So this was suggestive that maybe it's not a late time effect, but maybe something else. And then if you look at what's different from gravitational lensing, then what you see is that it's sensitive to small scale structure, and it's sensitive to structure on such small scales that the rearrangement of matter caused by active galactic nuclei and other energy injection mechanisms associated with structure formation can rearrange matter. So maybe there's no problem, and that it's just the effects of energy injection from structure formation. an alternative possibility is that maybe there's some funny property of the dark matter. But the point is that you're measuring things on different scales. So is it an early time, late time effect, or is it a small scale, large scale effect? With my colleague, Alex Salmon, we wrote a paper where we said, well, here's what you would need to do to the nonlinear spectrum to make it fit. And then it becomes a question of, disentangling it. Well, since then, there have been some very interesting developments. Lensing, measured the lensing of the cosmic microwave background. You can cross-correlate that with galaxy redshifts, with either galaxy redshift service or with galaxy catalogs. And this gives you a sort of handle on tomography. It means that you can test the growth rate of fluctuations at a lower redshift than the mean redshift of the lensing effect from the CMB light. Those analyses that have been done just in the last few months, they agree nicely with the standard lambda CDM cosmology. There are also, just in the last couple of months, 2 analyses looking at the numbers of rich clusters of galaxies. So this is based on eROSITA, an X-ray satellite, where people have looked at eROSITA of clusters that are calibrated using gravitational lensing. Their masses are calibrated using gravitational lensing. And then another analysis which uses Chandra X-ray measurements and, again, weak gravitational lensing mass calibrations. Those agree with the amplitude of the fluctuations expected from the lambda CDM cosmology. And so, in a matter of months, we'll see the results from the DESI redshift survey, which will improve the measurements of these distortions in redshift space measured from the galaxy distribution. And I don't know the results, but they should clinch it as that's overlapping the redshift range that lensing is sensitive to. So I'm hopeful that we'll have an answer of whether it's early time, late time physics, and so. And as you said, the tension is not as strong as the Hubble tension, and so the solutions might not need to be particularly radical.
Hey, it's me, your explorer of the universe from an experimental angle. I hope you're enjoying this conversation with George, and I want you to know I write about my conversations every single week in my Monday Magic mailing messages. It's a lot of M's, but it's for good use because I share with you the most mesmerizing ideas in all of science, technology, engineering, and math, and sometimes I do great giveaways. Like each month I give away a meteorite, a real piece of not dark matter, but ordinary baryonic matter from our early solar system, and you can win one too if you go to briankeating.com/list, and you're one of our lucky winners each month. But if you have a .edu email address and you live in the USA, you're guaranteed to win one of these beauties sent to you by the US mail, not by gravity. To enter to win, if you live in the USA and you have a .edu email address, go to briankeating.com/edu, and you're guaranteed to win one of these babies. Now, let's get back to the episode.
Another topic that is obviously near and dear to your heart and my heart as well is inflation. And there's also, some richness with controversy there as well. And I'm thinking of a couple of things. One is maybe late time and actually came from the Planck data set, which was a hint for negative curvature. I think Melchiorri's group and others have looked at this. So what is your take on this, the robustness of this measurement? So I recall it's a very small negative number, negative fraction of a percent, but it's more than a few sigma, so they take it seriously. How seriously do you take it, if at all? You're shaking your head.
Not very seriously. As you know, with the microwave background, you have a geometrical degeneracy. So there's a very strong degeneracy that just from the microwave background measurements alone, the only thing that breaks that degeneracy is the lensing of the cosmic microwave background. You are allowed a large range of curvatures, but it's asymmetric, so it extends into positively curved universes. The difficulty that some people have said that is 99% or whatever it is, some huge probability that that the universe is not exactly spatially flat. Significant curvature detected at 99% level. But the problem with that is that you're very sensitive to when you do this, you're very sensitive to prior choices. And I mean, I've written about this, that it's really badly motivated to, do analyses based on a flat prior, like a curvature, flat prior at the present day. I mean, choose a flat prior recombination and see what you get. I mean, so that's poorly motivated. So when you do this and the other thing is that there's been a massive shift over my career in the way you do statistics. When I was, first coming into the field, the statistical Bible was Kendall and Stewart, which was full of, frequentist tests and, student t-tests and all the sort of traditional stuff. And there's been a big shift to Bayesian statistics. So, it's not surprising because, if you've got Bayes' theorem at a big computer, you can solve any problem. I mean, but the problem is, how do you interpret Bayesian statistics? And on this, you should not be a fundamentalist Bayesian because priors matter. Okay, and they matter when you've got large degeneracies. In the case of early dark energy that we talked about earlier, there's a big degeneracy that you can, these models are, that you're compensating for changes in the Hubble constant by changing the slope of the fluctuation spectrum. So there's that big degeneracy there. And in the case of curvature, you have a geometrical degeneracy that from the CMB alone gives you a large degeneracy direction. So in that situation, you would be sensitive to priors, and numbers like 99% evidence in favor of curved universes are strongly dependent on the prior choices. So in problems like that, do a profile likelihood. That's the thing that you should do. March down the degeneracy direction and look at how chi-squared is changing. Okay, and if you do that, it doesn't change very much. So that's why I don't take these things very seriously. The other thing is that when you've got large degeneracies, combine with something that breaks the degeneracy. And this is easy to do, the CMB. Combine with baryon acoustic oscillations, with direct measurements of the CMB lensing potential. You break the degeneracy, and then you get exquisite limits. The universe is spatially flat to precision of few parts in 10 to the 3. I don't take that seriously. But you referred to the WMAT thing.
Yeah. So we're talking the 20th anniversary of your low anomalies. Yes.
This was great. So the WMAT results came out. There was some evidence that there was a lack of correlations on large scales compared to what you'd expect in a dark matter theory, an inflationary theory. So when I saw that, I thought, well, maybe you can relate that to some scale, and the obvious scale is curvature. Okay, so I wrote a quick paper trying to relate it to the curvature scale and what this would imply. And then I followed it up with another paper on the maximum likelihood measurement. And that convinced me that it wasn't really very significant. So, however, there are peculiarities, so-called anomalies on large angular scales. They've been examined in great detail. There's a really, really comprehensive paper by Ben Vandel and collaborators a few years ago that looked at a range of statistics of anomalies. So this included, correlations in the coefficients of multiple decompositions of the large-scale distribution on the sky. And the conclusion is that there isn't anything significant. I mean, there are anomalies, but they're not mind-blowingly significant. They're sort of 2.5 sigma level. So I think that even the most diehard inflationary theory, looking at the observations, would say our universe looks a bit odd on the large scale. But it's not so odd that, that people have said that it really challenges theory. It's just odd, but it could be telling us something interesting. And, the question is, can very, very difficult to make progress with something like this.
Pivoting back as we come to the top of the hour, the other controversy that arises with inflation is the sort of concomitant expectation or production of the multiverse. I've had on Andre Linde and Paul Steinhardt, Neil Turok, many, many other people debating Will Kinney, pro-multiverse, Andre Linde as well, and then many opponents to it, like Paul Steinhardt, as I mentioned. Talk to me about your impression. Is this really the purview of a cosmologist? I always say, kind of jokingly, that expecting a cosmologist to opine on the origin of the universe is like asking a zoologist to talk about the origin of life. They're related, and you might expect them to be answer the question more than a zoologist can answer a question about cosmology. But is the origin of the universe, is the origin of time, is the existence of a pre-existing or simultaneously existing universe, is that part of the project of cosmology that you and I practice?
The multiverse, the difficulty with the multiverse is that we don't have the theoretical background and machinery to say what happens in each of the realization of the multiverse. Okay, so we can't put a measure of the multiverse. And that means that you can't predict anything. Okay, so the thing that, the aspect that the Paul Steinhardt, Neil Turok really dislike is that if you cannot assign a measure to the multiverse, then your theories don't lack predictability, and therefore you don't know what you're doing. That problem is a really significant problem. So it's not crazy at all to be critical of the multiverse because it raises problems that we don't understand. Now, does that mean that inflation is wrong? And that's where I would, disagree with Paul Steinhardt and Neil. I don't think that means that inflation is wrong. It just means we don't, that inflation is we don't understand important aspects about inflation. I think with inflation, Ed Witten puts it very succinctly that inflation is attractive because for the amount of physics that you put in, you get a lot out, and you really do get a lot out. So does it mean it's right? Well, we don't know. Are there problems with the multiverse? Absolutely, there are problems. Undeniable problems with the multiverse.
March 17th, rather. And that was a very, very, very important day in my life because that was the day 10 years ago we released the BICEP2 results. And I think we're coming on a decade of it. I never, we talk, about nuts and bolts and funding and all sorts of requests and stuff that we on the Simons Observatory experimentalist team and analysis team make to the external advisory committee that you're a key member of. But we really never talked about, what was going through your mind when we released these results. And have you, I tried to portray some of what I thought about your impressions of the affair in my book, Losing the Nobel Prize. I don't know if I quoted you appropriately, but we were sort of terrified of you and the Planck satellite just on the internals. And we had read a paper, and I mentioned this in the book, by you. I think you're the first author, forecasting in 2009 or 2010, right when BICEP2 went online at the South Pole, that you would achieve a level that would able Planck to detect what we claimed as R of 0.2 at 4 or 5 sigma. And, in the end, I think you recently had a paper about B modes from Planck at low L's, but we'll talk about that maybe at the very end. But what was going through your mind when we released that and kind of on the inside as a professional competitor?
It became very clear, during the early stages of Planck that these forecasts were wildly optimistic. So there were systematic effects in Planck that would limit our ability to set tight limits on B modes. I mean, it's sort of mundane stuff, if you like. The way that the bolometer signals were converted, from analog signal to a digital signal, introduced systematics in the data that were difficult to disentangle from mother systematics. So, the polarization is a differencing measurement. It's trying to measure a very small signal, and if you've got fluctuations in your detection baseline, then that's a severe problem. There were heroic efforts to remove these systematics, and in the end, with Planck, you can set a limit of a tensor to scalar ratio of about 0.3 or whatever, a little bit higher than the bicep detection. Now, when the bicep detection was first announced, I mean, I was really taken with the shape of the spectrum and that it fitted primordial gravitational waves. The amplitude was high because we'd already set limits on simple modes of inflation, and the 0.2 was high compared to the Planck results. There was then a flurry of papers, really just quite low grade papers explaining, modifying them, and so on. But then our dust colleagues, we had a telecon. Our dust colleagues said, look, that region, it could all be dust. And, this isn't very difficult because, to check with Planck, because, we had 353 gigahertz polarization. And so it became very clear that dust was a problem. But 353 was not high enough signal to noise to clinch it. So that's when we proposed the bicep-Planck collaboration, so that we could do the cross-correlations, because then if you do the cross-correlations with the bicep data, you prove the signal to noise, and then that clinched it as, dust could explain the entire signal. It was really interesting because with the announcement, I thought, this, if it's correct, this is really, really great. And it was a shame that it didn't pan out. But that's science. Now what is the value of the tensor to scalar ratio? Who knows? You could struggle for the next 10 years and not make a discovery. So
yeah, we may indeed. But luckily with the Simons Observatory, we have many ancillary and, quite frankly, just as interesting science quarries. And you are undoubtedly going to play a key role in making sure we stay on the right track.
Yes, so there's still an incredible amount. One of the things that I like about the cosmic microwave background is that, if you can make the measurements, then on the whole, the interpretation is quite, is simpler than looking at astrophysical objects. So you should milk it for as much as you can, and you will, with Simons, you'll end up with foreground modeling, complicated foreground modeling for lensing and, other things that, you have to deal with to extract the science. But it's still one of the best probes of cosmology, one of the best tests of cosmology that we have. There's a lot of information to be gained.
Absolutely. So, George, I have a tradition on this podcast that I always ask one kind of metaphysical or existential question or more, sometimes inspired by Sir Arthur C. Clarke, who gave us the name of this podcast by saying the only way of determining the limits of the possible is to transcend those limits and go into the impossible. But instead, I'm going to use one of his other favorite quotes, which is any sufficiently advanced technology is indistinguishable from magic. And I want to get your reaction to what Richard Feynman called the cataclysm question. And he would ask scientists to tell him what would be the most important or interesting or most power-packed phrase or knowledge that human beings in our whole species history have gleaned about the universe, such that we could really say that we accomplished something magical. I want to ask you, if you were to make sort of a time capsule, a billboard for planet Earth, what would you say is the most important, interesting, fascinating discovery, whether it be in science or in life, and anything you want? What would be sort of something you'd put on a time capsule to last for all eternity?
I think that the most miraculous thing, from my perspective, and it's incredible that we have observational evidence to support it, is that the entire observable universe, everything that we see, with our big telescopes and everything, our entire observable universe has a quantum origin. That quantum mechanics have affected, the very largest scale. And that is, that's an astonishing. I find it astonishing. Well, if a civilization hasn't figured that out, then that's a good thing to know.
George, this has been such a delight. Professor at University of Cambridge, first director of the Kavli Institute for Cosmology, leader of the Planck science team, just an all-around mentor and friend of the cosmos. I want to thank you so much for staying up late over there in the UK. I really appreciate it. I know you've had a long day. And I just want to say I appreciate so much your work on behalf of getting things right. We can't afford to make another mistake in this field. And it's absolutely crucial that you and all the good-natured and good-hearted and good-intentioned people will hold the experimentalist feet to the fire, but also accept criticism from us when we do mount it. Because I think only in that kind of partnership can we achieve a consilience that allows us to really solve the most fascinating mysteries I think that human brains can contemplate, which is how did our universe get to be the way it is?
Thank you very much.
Hey there, congratulations, you watched all the way to the end. And I know you're going to love this conversation with the hilarious and brilliant Michael Turner, the man who came up with the term dark energy. And click here for a playlist of the best episodes covering cosmology on the Into the Impossible podcast. See you next week.